Hello dear students, all of you welcome to Vidyan classes. Today we will discuss inverse of a square matrix. In matrix chapter, we have read the definition of inverse of a square matrix. Here we will discuss a theorem, that is theorem number 2. It is defined by a square matrix capital A is invertible if and only if A is non-singular. If and only if means implies and implies by. A is non-singular, that means determinant of A not equal to 0. For a singular matrix, determinant of A is equal to 0. A is invertible implies A is non-singular. A is non-singular implies A is invertible. This implies to this and this implies to this. Clear? Let capital A be the invertible matrix of order n, and capital I be the unit matrix of order n. Let capital A be the invertible matrix of order n and capital I be the unit matrix of order n to show A is non-singular. Matrix. A is invertible matrix implies A is non-singular. That is dA is equal to dA means determinant of A not equal to 0. Since capital A is invertible, the square matrix capital A is invertible. It is given A is invertible. That implies A inverse is exist. A inverse is exists. Since A is invertible implies A inverse is exists. By the definition of inverse of a square matrix, by the definition of inverse of a square matrix, there exists a square matrix capital B of order n satisfying AB is equal to BA is equal to I. Since A is invertible, that means that implies A inverse is exist. By the definition of inverse of a square matrix, there exists a square matrix capital B of order n satisfying AB is equal to BA is equal to I. It is the definition of inverse of a square matrix. We have read in matrix chapter. Clear? B is the inverse of A. A inverse is exist. B is the inverse of A. That implies determinant of AB is equal to determinant of I. Since AB is equal to I, that implies determinant of A into determinant of B is equal to determinant of I is equal to 1. Since determinant of AB is equal to determinant of A into determinant of B, where A and B are the square matrices of same order. It is defined by determinant of AB is equal to determinant of A into determinant of B, where A and B are the square matrices of same order, and determinant of unit matrix is equal to 1, that is unit. Determinant of AB is equal to determinant of A into determinant of B. Determinant of unit matrix is equal to 1. Clear? Which implies determinant of A into determinant of B is equal to 1. The product of this into this, product of this and this is equal to 1 implies determinant of A not equal to 0. Since the product is 1, A not equal to determinant of A not equal to 0. That implies determinant of A not equal to 0 implies the matrix capital A is non-singular. Implies A is non-singular. A is non-singular matrix. A is invertible, therefore A is invertible. A is invertible. Implies A is invertible matrix. Implies A is non-singular matrix. Case 1 is proved. The first part is proved. A is invertible implies A is non-singular. Clear? Okay. Next, A is non-singular implies A is invertible. Conversely, let capital A be a non-singular matrix. That is, determinant of A not equal to 0. To show capital A is invertible. Conversely, let A is non-singular. We have to prove A is invertible. The inverse of A is exists. To show A is invertible. Clear? This implies to this. A is non-singular matrix implies A is invertible matrix. Invertible matrix. In theorem 1, we have A into Rj is equal to Rj into A is equal to A determinant into I the unit matrix or identity matrix. In theorem 1, we have A into Rj is equal to Rj into A is equal to A determinant into I. That implies A into Rj divided by determinant of A, which is same as Rj into A divided by determinant of A is equal to I. Dividing A determinant at each term, dividing A determinant. Since A is non-singular, that means A determinant not equal to 0. Clear? So we can divide A determinant. That implies A into Rj divided by A determinant. Rj and A divided by A determinant into A is equal to I. Is the form of AB is equal to BA is equal to I. AB is equal to BA is equal to I. It is the definition of inverse. AB is equal to BA is equal to I. That implies B is the inverse of B is equal to A inverse. Here B means in the form of AB is equal to BA is equal to I. It is the definition of inverse of the square matrix. A is the square matrix to show A is invertible. Since it takes the form of AB is equal to BA is equal to I, we can say B is equal to A inverse. Implies B is equal to Rj divided by A determinant is equal to A inverse. Clear? Since it takes the form of AB is equal to BA is equal to I, it is the definition of inverse of the square matrix capital A. So B is the inverse of A. B is the inverse of A. Here B means adjoint A divided by A determinant. Here B is equal to Rj divided by A determinant is equal to A inverse. Hence the inverse is exists. Therefore A is a non-singular matrix. Therefore A is a non-singular matrix implies A inverse is equal to A inverse exists. That means A is invertible and A inverse is equal to adjoint A divided by A determinant. Hence proved. A is invertible implies A is non-singular. A is invertible implies A is non-singular matrix. Conversely, A is non-singular matrix implies A inverse exists. Clear? Therefore, is the form of the A is non-singular implies this. Hence, the statement is proved. A square matrix is invertible, that implies A is non-singular. A is non-singular implies A is invertible. Hence, the statement is proved. Clear? Okay, write down. Question number 1. So that the matrix capital A having elements 2, 3, 1, 2 satisfies the equation A square minus 4A plus I is equal to 0 matrix, where I is the identity matrix of order 2 and capital O represent the 0 matrix of order 2. Using this equation, find A inverse. Case 1. First, we will prove A square minus 4A plus I is equal to 0 matrix when A is equal to matrix having elements 2, 3, 1, 2. LA side for A is equal to 2, 3, 1, 2 A square minus 4A plus I. A square means A into A. A is given by 2, 3, 1, 2 minus 4, 2, 3, 1, 2 plus identity matrix I. It is A square, which is same as 2, 2, 3, 1, 2 into 2, 3, 1, 2 minus 4 is a scalar plus minus 8 minus 12 minus 4 and minus 8 plus unit matrix I. Whenever a scalar is multiplied with a matrix, it will be multiplied in each element of the given matrix. Minus 8, minus 12, minus 4, minus 8. Multiplication of this and this. It gives by the matrix multiplication rule, go through row 1, come down in column 1, multiply the corresponding elements and add them. 2 into 2 that is equal to 4, 3 into 1 that is equal to 3, 2 into 3 that is equal to 6, 3 into 2 that is equal to 6, 1 into 2 is equal to 2, 2 into 1 that is equal to 2. 1 into 3 that is equal to 3, 2 into 2 that is equal to 4, plus minus 8, minus 12, minus 4, minus 8, plus capital I is the identity matrix of order 2. So its elements are 1, 0, 0, 1. Which is equal to 7 plus 12, 7 plus 7, 12, 4, 7 plus minus 8, minus 12, minus 4, minus 8 plus 1, 0, 0, 1. Which is same as addition of the matrices is the addition of their corresponding elements. 7 minus 8 plus 1. Addition of matrices is the addition of their corresponding elements. First. That is 7 minus 8 plus 1. 12 minus 12 plus 0. 12 minus 12 plus 0. 4 minus 4, 0. 4 minus 4 plus 0. 7 minus 8 plus 1. Which is same as 7 plus 1 minus 8 that is equal to 0. 12 minus 12 that is 0. 4 minus 4 that is 0. 7 plus 1 minus 8 is 0. Which equal to 0 matrix. Capital O represent the 0 matrix. All elements are 0. It is a 0 matrix. Which equal to RH side. LH side is equal to RH side. Therefore, A is equal to A is the matrix having elements 2, 3, 1, 2 satisfies the equation A square minus 4a 4i a square minus 4a plus I is equal to 0 matrix. The first part is proved. The first part is proved. That is, hence case 1 is proved. Case 2, using this equation find A inverse. Case 2, using this equation, A is the given matrix having elements 2, 3, 1, 2. Implies yes, determinant of A is equal to 4 minus 1, 4 minus 3, that is equal to 1, not equal to 0. Implies yes, since A determinant not equal to 0, A inverse is exist. Since A inverse is equal to Rj divided by A determinant. Since A is non-singular, A inverse is exist. We have to find out A inverse using the equation. We have to find out the inverse of A using the given equation. A square minus 4a plus I is equal to 0 matrix, which implies as A square minus 4a is equal to minus I. Clear? A square minus 4a is equal to minus I. Clear? Okay. A square minus 4a into A inverse minus I into A inverse. Matrix multiplication satisfies the closure law. Minus I is equal to this. Since A determinant not equal to 0, A inverse is exist. Which is same as A square into A inverse minus 4a into A inverse, which is equal to minus I into A inverse. Since matrix multiplication is distributive, matrix multiplication is distributive. Since A plus B into C is equal to AC plus BC. Matrix multiplication is distributive, which implies this A square can be written as A into A into A inverse minus 4 A into A inverse minus I A inverse. Since alpha AB is the same as alpha A into B, Matrix multiplication is associative with respect to scalar. So this can be written as this. Clear? Which is same as A into A inverse minus of 4 A inverse, which is equal to minus I into A inverse. Matrix product is associative. A BC is equal to AB. Clear? Which implies this A into A inverse is equal to I minus of 4 A into A inverse is equal to I is equal to minus I A inverse, which is same as A minus of 4I is equal to minus A inverse. Since A into I is the same as I into A is equal to A, which is same as A inverse is equal to 4I minus A. A inverse is equal to A inverse is equal to 4I minus A, which is same as 4I means 1 0 0 1 minus A means 2 3 1 2, which is same as 4 0 0 4. 4 is a scalar. Minus of this is same as minus 1 is a scalar. If a scalar is multiplied with a matrix, then it will be multiplied with the given matrix. Minus 2, minus 3, minus 1, minus 2. Since minus A is equal to minus 1 into A. Minus 1 is the scalar. Addition of two matrices is the addition of their corresponding elements, which is equal to 4, 4 minus 2, 0 minus 3, 0 minus 1, 4 plus minus 2. 4 plus minus 2 is equal to 4 minus 2, which is same as 2 minus 3 minus 1 and 2. A inverse means place change, sign change. A inverse, by the direct method we can find out A inverse. A inverse means place interchange of the diagonal elements. 2 and 2 are interchanged, and the sign changes of 3 and minus 1, which gives this, which is equal to A inverse. Therefore, A inverse is equal to 2 minus 3 minus 1 and 2. Clear? Clear? Okay, write down. Direct method to find A inverse where A is a non-singular matrix of order 2. Let capital A be the matrix having elements A, B, C, D of order 2. 2 cross 2 means order 2. Implies as determinant of A not equal to 0. That means A is non-singular. Implies as determinant of A, that means AD minus BC. AD minus BC not equal to 0. Clear? Determinant of A, AD minus BC not equal to 0. That means A is non-singular. A is, that is A is non-singular. A inverse is defined by Rj divided by A determinant. Which is same as Rj means place interchange of A and D. We have discussed it is the place interchange of A and D. Place interchange of A and D. Place interchange of the diagonal elements, that is A and D, and sign interchange of B and C. Sign change of B and C. Rj is given by place interchange of A and D. D, it is A. Change of sign of B and C. Minus B and minus C. So A inverse is equal to Rj divided by A determinant. Rj is given by D minus B minus C A divided by A determinant. A determinant means AD minus BC, which is not equal to 0. So it is the direct method to find the inverse of capital A, where capital A is a non-singular matrix. That means determinant of A not equal to 0. Example, let capital A is a matrix of order 2 having elements 2, 3, 4, 5. A determinant is equal to 10 minus 12. 10 minus 12, that is equal to minus 2, not equal to 0. That means A is non-singular. So A inverse is exists. A inverse is defined by Rj divided by A determinant. By the direct method, we can find out adjoint of A, place interchange of 2 and 5. It gives 5, 2. Place interchange. Sign change of 3 and 4. Minus 3, minus 4. Divided by A determinant. which is the same as minus 2, which is same as 5 by minus 5 by 2, 3 by 2, it is 2 and it is minus 1. Minus half is a scalar. If a scalar is multiplied with a matrix, then it will be multiplied in each element of the given matrix. Minus 5 by 2, minus plus 3 by 2, minus 4 divided by minus 2, that is 2. 2 by minus 2, that is equal to minus 1. Therefore, A inverse is equal to minus 5 by 2, 3 by 2, 2 minus 1. Clear? Another example. Let A be the given matrix having elements 3, 5, 1 and 2. Suppose it is minus 3, minus 2. Implies A determinant is equal to 6 minus 5 equal to 1. Not equal to 0. A inverse is exist. A inverse is equal to place interchange of the diagonal elements. That is minus 2 minus 3. Change of sign of 1 and 5. Minus 5 minus 1. Divide by a determinant, that is equal to 1. Which is equal to minus 2 minus 5 minus 1 and minus 3. It is the inverse of A. Right. Therefore, A inverse is equal to minus 2 minus 5 minus 1 minus 3 is the answer. Clear? Okay, write down. Question number 2. If capital A is a square matrix of order 2 having elements 3, 1, minus 1, 2, so that A square minus 5A plus 7I is equal to 0 matrix, where I is the unit matrix or identity matrix of order 2 and capital O is the 0 matrix of order 2. Hence find A inverse. Hence find A inverse means using this equation we will find A inverse. Clear? Hence find A inverse means using this equation we will find A inverse. There are two cases. First, we have to prove A square minus 5A plus 7I is equal to 0 matrix. Then to find A inverse. Case 1. Case 1. To show A square minus 5A plus 7I is equal to 0 matrix. For A is equal to, A is the matrix having element 3, 1, minus 1, 2. To show it is a 0 matrix. LI side A square minus 5A plus 7I, which is same as A into A minus 5A plus 7I. A means A is the matrix having elements 3, 1, minus 1, 2 into 3 1 minus 1 2 minus 5a plus 7i. By the matrix multiplication rule, go through row 1, come down in column 1, multiply the corresponding elements and add them. Go through row 1, come down in column 1, multiply the corresponding elements and add them. 3 into 3 that is equal to 9, 1 into minus 1 that is equal to minus 1, 3 into 1 that is equal to 3, 1 into 2 that is equal to 2. Next, go through row 2, come down in column 1 that is minus 3, minus 2, minus 1, plus 4, minus 5, A means 3, 1, minus 1, 2, 7, I the unit matrix of order 2. Its elements are 1 0 0 1. It gives 8 5 minus 5 and 3 plus minus 5 is a scalar. If a scalar is multiplied with a matrix, then it will be multiplied with each element of the given matrix. It gives minus 15, minus 5, 5 and minus 10. Minus 15, minus 5, plus 5, minus 10. Plus 7 0 0 7, which is a match. Addition of matrices is the addition of their corresponding elements. 8 minus 15 plus 7. Addition of matrices is the addition of their corresponding elements. 5 minus 5 plus 0. Addition of matrices is the addition of their corresponding elements. Plus 0. 3 minus 10 plus 7, which is same as 8 plus 7 minus 15 that is equal to 0. 5 minus 5 is 0. 5 minus 5 is 0. 10 minus 10 that is equal to 0, which is a 0 matrix of order 2. Clear? Which is equal to array site. Array site is equal to array site therefore a square is equal to 5a plus 7i is equal to 0 matrix. Hence, case 1 is proved. Hence, case 1 is proved. Hence, find A inverse. It is the second case. It is the second case, case 2. To find A inverse using this equation, a square minus 5a plus 7i is equal to 0 matrix. is equal to 0 matrix, which implies a square minus of 5a is equal to minus 7i. That means adding minus 7i both sides. A square minus 5a is equal to minus 7i. Since determinant of a, that is equal to 6 plus 1 is equal to 7, not equal to 0, implies A inverse EG exists. A inverse EG exists. Since a determinant not equal to 0, A inverse is defined by adjoint divided by A determinant. It is a star. Star implies a square minus 7a into A inverse. A inverse is exist. So we can multiply A inverse minus 7i into A inverse, which is same as A square means A into A into plus minus of 5a into A inverse, which is equal to minus 7i into A inverse. Subtraction to matrices is the addition of one with the negative of other, which implies A into A inverse plus minus of 5a into A inverse is equal to minus 7i into A inverse. Since A plus of B into C is equal to AC plus of BC. Matrix multiplication is distributive. It is the right distributive law. Using right distributive law, this can be written as this, which is same as A into A inverse plus minus 5 into A inverse is equal to minus 7 I into A inverse. Clear? Since AB into C is equal to ABC, alpha into AB is equal to alpha A into B. Matrix multiplication is distributive with respect to matrices. Also it is matrix multiplication is associative with respect to matrices. Also it is associative with respect to scalar. Here alpha is a scalar. ABC are the matrices. Matrix product is associative with respect to matrices, also associative with respect to scalar. So this can be written as this can be written as this can be written as this, which implies A into I plus minus 5 into I is equal to minus 7 I into A inverse. Since A into A inverse is equal to I, which is same as A inverse into A, which is same as A plus minus 5i. A plus minus 5 into I is equal to minus 7 A inverse. Since A into I is equal to I into A is equal to A. So this can be written as this is written as this. We have to find out the inverse of A inverse, which is same as minus 1 by 7 A plus minus 5 I is equal to minus 1 by 7 I 7 into A inverse minus 7 into A inverse, multiplying minus 1 by 7 both sides, which is same as A inverse is equal to A inverse minus 1 by 7 minus 7 A inverse, which is equal to A inverse minus 1 by 7 A plus minus 5 into I. Clear? Okay. A inverse is equal to minus 1 by 7 into A means 3, 1, minus 1, 2. 3, 1, minus 1, 2. Minus 7 I means unit matrix of order 2. I the unit matrix of order 2. 1, 0, 0, 1. Minus 5i is equal to minus 5, 0, 0, minus 5. Minus 5i. That is minus 5, 0, 0, minus 7. Which is same as minus 1 by 7. Addition of matrices is the addition of their corresponding elements. 3 minus 2, minus 5, that is minus 2, 1 plus 0, that is equal to 1, minus 1, 0, that is minus 1, 2 minus 5, that is minus 3. Place interchange of 3 and 2. Place interchange, which is same as taking minus 1 common, that is 1 by 7, taking minus as a common, or minus 1 is multiplied with this, that is 1 by 7, 2, minus 1, 1 and 3. Place interchange. By the direct method, we can find out A inverse. Place interchange of 3 and 2, which gives 2, 3. Sign changes of 1 and minus 1, that is minus 1 and 1. So it is correct. Is equal to this. Is the inverse of it is the inverse of A. A inverse is equal to 1 by 7, 2 into this, which is same as 2 by 7, minus 1 by 7, 1 by 7, and 3 by 7. Therefore, A inverse is equal to 2 by 7, minus 1 by 7, 1 by 7 and 3 by 7 is the answer. Clear? Are we clear? Okay. Note down. Question number 3. Let capital A be the square matrix of order 2 having elements 2, 3, minus 1, 5. If A inverse is equal to XA plus Y I2. I2 means unity matrix or identity matrix of order 2. Then find X and Y. Given capital A is the square matrix of order 2 having elements 2, 3, minus 1, 5. Which implies yes, a determinant is equal to 10 plus 3 which is equal to 13 not equal to 0. That means A is non-singular. Implies yes, A inverse is exists. A inverse is exists since A is non-singular. A inverse is equal to X into A plus Y into I2. A inverse is defined by adjoint A divided by A determinant XA plus Y I2. Adjoint A is given by, it is a square matrix of order 2. So we can find out A inverse by the direct method. Place interchange of the diagonal elements. It gives 5, 2. Sign change of 3 and minus 1. It is a minus 3 and 1. Divided by A determinant is equal to 13. AXA, it gives 2x, 3x, x is a scalar. If a scalar is multiplied with a matrix, then it will be multiplied with each element of the given matrix. 2x plus 3x minus x, 5x plus y into I2. I2 means unit matrix or identity matrix of order 2. Order 2. 1, 0, 0, 1. Y is the scalar. Y into I2 gives y, 0, 0 and y. Clear? Y into I2, which is same as addition of two matrices is the addition of their corresponding elements. It gives the matrix having elements 2x plus y, 3x plus 0, minus x plus 0, that is minus x, minus x plus 0, 5x plus y. Clear? 1 by 13 is a scalar. Multiplying with this matrix, it gives 5 by 13, 1 by 13 into 5, that is 5 by 13, minus 3 by 13, 1 by 13, 2 by 13 is equal to 2x plus y 3x minus x 5x plus y. Clear? Okay. Two matrices are equal. Two matrices are equal if their corresponding elements are equal. Implies this 2x plus y is equal to 5 by 13. 3x is equal to minus 3 by 30. X is equal to 2 by 13. X is equal to x equal to 1 by 13. X is equal to 1 by 13 minus 1 by 13. And 5x plus y is equal to 2 by 13. Two matrices are equal if their corresponding elements are equal. Implies this x is equal to minus 1 by 13. Y is equal to 5 by 13 minus 2x, which is equal to 5 by 13 minus x is equal to minus 2x plus 2 by 13, which is equal to 7 by 13. Therefore, x is equal to minus 1 by 13 and y is equal to 7 by 13. Clear? Okay, write down. Question number 4. Let capital A and capital B are two square matrices of order 2. Verify AB inverse is equal to B inverse into A inverse. Given capital A is the matrix having elements 3, 7, 2, 5. Implies this A determinant is equal to 15 minus 14, that is 1, not equal to 0. And capital B is the matrix having elements 6, 8, 7, 9. 54 minus 56. 54 minus 56, that is equal to minus 2, not equal to 0. Implies this A not equal to 0, B not equal to 0. So, A inverse, B inverse are exists. A is non-singular and B is non-singular. So, A inverse and B inverse are exist. AB is equal to 3, 7, 2, 5. B is the matrix having elements 6, 8, 7, 9. By the matrix multiplication rule, go through row 1, come down in column 1. It gives 3 into 6, that is 18. 3 into 6, that is 18. 7 into 7, 49. 3 into 8, 24. 7 into 9, 63. 2 into 6, 12. 5 into 7, 35. 2 into 8 that is 16, 5 into 9 that is 45. Clear? 3 into 6 that is 8, 18, 7 into 7 49, 3 into 8 24, 7 into 9 63, 2 into 6 12, 5 into 7 that is 35, 2 into 6, 2 into 8 equal to 16, 5 into 9 45, which is equal to 18 plus of 49. It gives 67. 24 plus of 63, that is 87. 12 plus 35, 47. 16 plus 45, it gives 61. Clear? Which implies determinant of AB is equal to 67 into 61 minus 87 into 47. 67 into 61, it gives 42. 6 into 6 36 plus 4 that is equal to 40. 7804. 87. 87 into 47. 87, 47, 49, 56 plus 4 that is 60. 28, 34. 4 into 7, 28. 4 into 8, 32 plus 2 that is 34. 9, 8, 0, 4. It gives this into this, that is 47. 4087 minus 4089, which is equal to minus 2, not equal to 0. Clear? Minus 2 not equal to 0. Determinant of AB not equal to 0 implies AB inverse EG exists. AB inverse EG exists. AB inverse. AB is a square matrix of order 2, so we can find out by the direct method. Place interchange of the diagonal elements. Place interchange of the diagonal elements. It gives 61, 67. Place interchange of the diagonal elements. Sign changes of 47 and 87. Minus 47 and 80 minus 87. Divided by A determinant. Divided by A determinant. A determinant is given by minus. AB determinant. That means arcs AB divided by adjoint of AB divided by determinant of AB. It is the inverse of AB. Next, B inverse into A inverse. B inverse into A inverse. B is a square matrix of order 2. So we can find out the inverse by the direct method. That means adjoint of B divided by B determinant into adjoint of A divided by A determinant. Which is same as adjoint of B, place interchange of 6 and 9. 9, 6. Sign change of 8 and 7. Minus 7. Divided by A determinant. 54 minus 56 minus 2. Minus 2 into adjoint of A, place interchange of the diagonal elements, that is 5, 3. Sign changes of 7 and 2. Plus will be minus and minus will be plus. Divided by A determinant. A determinant is equal to 1. Which is same as minus half into 9 into, by the matrix multiplication rule, 9 into 5, that is 45 plus 16. 9 into 5, 45 minus 8 into minus 2, that is 16. Next, 9 into minus 63, minus 63, minus 24. Go through row 1, come down in column 1, then column 2. Next, go through row 2, minus 35, minus 12, minus 35, minus 12, 49 plus 18. It gives minus half into 61. 61. It is 61. Next, 8 minus 87. It is minus 87. Next, minus 47. And 67. 67. Which is same as this, is equal to AB inverse. AB inverse. AB inverse is given by this. Therefore, AB inverse is equal to B inverse into A inverse. Therefore, the statement is verified that true. AB inverse is given by this, and B inverse into A inverse is also same as this. Clear? Okay. Note down.